In this video, we're going to talk about linearly dependent and independent sets of vectors. Again, this will be reviewed if you encountered this concept in linear algebra. The only difference is we're doing this over an arbitrary field now. So here's a definition. Let's as always, let V be a vector space over F, a field. All right, and let S be a set of vectors in V. So S is a subset of V. We say S is linearly dependent if there exist vectors and I'll call them V1 through Vn in S, so finitely many vectors, and scalars alpha 1 through alpha n belonging to F, not all 0, such that the linear combination alpha 1 V1 plus etc. through alpha n Vn is equal to the 0 vector. A slightly more concise way to say that is there is a non-trivial linear combination of vectors in S that is equal to 0. By non-trivial, I mean that we are combining the vectors in such a way that we're not just combining 0 of everything, because if we combine 0 of everything, then of course we should expect the sum is going to be 0. So we're saying that there is some way of combining the vectors so that we're not taking 0 of everything, and yet somehow we're getting back to 0. All right, one more little part to the definition. S is linearly independent if it is not linearly dependent. And sometimes if we are doing work in field theory where we might switch from one subfield to another as our field of scalars, I might add the little embellishment linearly dependent over F or linearly independent over F. That's if we're doing work where we are considering a field like an extension field as a vector space over one subfield, but maybe also over another subfield at the same time. Okay, so that's the definition of linearly dependent, linearly independent. Let's do an example. I'm getting kind of bored with the example of C as a vector space over R, so let's try something different. Let's consider the field extension H equals Q adjoin the square root of 2 over the field of rationals. So Q adjoin root 2 is a vector space over the rationals. And consider the set let's say 1 square root of 2 plus 1 and 2 square root of 2 plus 1. Those are all elements of Q adjoin root 2. Now I claim that this set is linearly dependent over Q. And we can show that. So here's why. I know that 2 square root of 2 plus 1, just in looking at this set, I know that I am going to be able to write that as a linear combination of the other two over the rationals. And here's how I'd do it. I would write it as 2 times root 2 plus 1, that's my second vector, and then that would give me 2 root 2 plus 2, so I'm going to make up for that by subtracting 1, or more precisely by multiplying negative 1 times 1. So here I've managed to write one of my vectors, the third one, as a combination of the other two. Now that's not exactly my definition. My definition says that my set's dependent if there's a non-trivial linear combination of the vectors that is equal to 0, and that's not exactly what I've done. But I can retool this into that. I can take this equation here and move these two terms here, this one and this one, to the other side. So rewrite that as 1 times 1, so I'm just subtracting both of those terms from the right, plus negative 2 root 2 plus 1 plus 1 2 root 2 plus 1. So if these are my vectors v1, v2, and v3, then my alpha 1 is 1, my alpha 2 is negative 2, and my alpha 3 is 1. And you can verify that that does indeed equal 0, and that's a non-trivial linear combination of my three vectors that gives me the 0 vector. Okay, so that means that this set is dependent. In other words, not independent. Okay, let's try another one. Okay, what about the set 3 plus 4 root 2 and 5 minus root 2? Both of those are elements of Q adjoin root 2. I will show this set as independent. Well, how do I show that a set's independent? Well, I show that it's not dependent. What does it mean to show the set's not dependent? It means we show that there does not exist a set of scalars alpha 1 and alpha 2, not all 0, such that alpha 1 this plus alpha 2 times this equals 0. All right, so equivalently, we need to show that if there are scalars alpha 1 and alpha 2 in the rationals, such that alpha 1 3 plus 4 root 2 plus alpha 2 5 minus root 2 equals 0. If that's true, sorry, that shouldn't be an if there. Okay, if alpha 1 and alpha 2 are rationals satisfying that, then alpha 1 and alpha 2 both are equal to 0. In fact, I'll just put an equal sign there for emphasis. All right, that's what we need to show. And we can actually prove that just using linear algebra by solving a system of equations. All right, so if that is true, so let's assume alpha 1 and alpha 2 are rationals, such that alpha 1, 3 plus 4 root 2, plus alpha 2, 5 minus root 2, all that is equal to 0. Well, if that's the case, then I can gather up my rational terms and get 3 alpha 1 plus 5 alpha 2, and then say that plus, let's see, 4 alpha 1 minus alpha 2 times the square root of 2, I'm gathering up all my root 2's now, that equals 0. All right, one thing that I know is that if I were to move the right term over, I would get, this is just a little side note here, 3 alpha 1 plus 5 alpha 2 equals alpha 2 minus 4 alpha 1 times the square root of 2. And I would get the root 2 equals 3 alpha 1 plus 5 alpha 2 over alpha 2 minus 4 alpha 1, which seems outrageous because the expression on the right is a rational number, and square root of 2 isn't. Square root of 2 is not rational. Okay, but here's the thing. All of that I just did, including dividing by alpha 2 minus 4 alpha 1, this assumed the denominator was non-zero. All right, so if that denominator is non-zero, then I show that square root of 2 is a rational number. That's a contradiction. So this means alpha 2 minus 4 alpha 1 has to equal 0, which means for this whole equation to be true here, if this is 0, then that also has to be 0. And now I get my system of linear equations over the rationals. 3 alpha 1 plus 5 alpha 2, that has to be 0. Let's see, 4 alpha 1 minus alpha 2, I'm going back to the original order of the variables here, that also has to equal 0. And so now I can just solve this system. If I take this equation here and multiply both sides by 5, that's another valid equation, and I can add those up, and I get, I think, 23 alpha 1, that's kind of weird, and then the alpha 2's cancel out, and I get 0. So that means alpha 1 ends up having to be 0. So if I substitute that into my first equation here, that means that 5 alpha 2 is also 0, so alpha 2 also is equal to 0. All right, so what did I just show? I showed that if I have some linear combination of 3 plus 4 root 2 and 5 minus root 2 equals 0, the only way that occurs is if the two coefficients, the two scalars, are 0. That means that this set is independent. Since only the trivial linear combination gives the 0 vector. All right, so that's an example of an independent set. But here's the part that's kind of crazy, and the reason why we need to talk occasionally at least about over what field we are having the discussion. So one more example. This time, let's consider Q adjoin root 2 as a vector space over itself. That's perfectly valid. Any field is a vector space over itself. And in this case, the set, what was it again? It was 3 plus 4 root 2, 5 minus root 2. This time, this set is linearly dependent. Okay, here's why. I know from previous theorems, because I get Q adjoin root 2 by modding Q bracket x by a maximal ideal, the ideal of x squared minus 2, I know this is a field. So that means that 3 plus 4 root 2 can be written as 5 minus root 2, all of that times the following expression, 3 plus 4 root 2 over 5 minus root 2. And because 5 minus root 2 is non-zero, I know that that has a multiplicative inverse. So I can actually take the value of that expression, that is something in Q adjoin root 2. If it makes you feel better, we could rewrite that as 5 minus root 2 times 3 plus 4 root 2 times the inverse of 5 minus root 2. That might be a more proper way of saying that. So anyway, what that means is that I can write 1 times 3 plus 4 root 2. And then what do I have then? I have minus this scalar, 3 plus 4 root 2, 5 minus root 2 inverse, all of that times 5 minus root 2. Okay, so that's a linear combination, a non-trivial linear combination of 3 plus 4 root 2. That's V1 and V2, which is 5 minus root 2. And that's all equal to 0 because I took these two things which were equal, 3 plus 4 root 2, and this is also 3 plus 4 root 2, and I subtracted those. Sorry, hungry cat in the background. Anyway, this is a non-trivial linear combination. The scalars do belong to Q adjoin root 2. That's why I couldn't do this last time, as last time my scalars had to come from the rationals. This time they come from Q adjoin root 2. But this is a non-trivial linear combination that's equal to 0, and therefore this set is dependent. So that's why thinking about the base field, or the field of scalars, is important.